Hello, we are Team 20, TPMS Signal Demodulation. We are Chris Fusaro, Dutch Kip, Kasper Kolesha, and David Shi. The main objective of this project was to see if it is possible to uniquely identify vehicles that are outfitted with a tire pressure monitoring system, or TPMS. Our client, Nate Gergen, has a patent that utilizes vehicle identification in different ways. These systems consist of 4 pressure sensors, one within each tire of a vehicle, that communicate wirelessly with the engine control unit and notify the driver of tire pressure within each tire. Each sensor has a unique serial number so that the engine control unit can differentiate between tires. There are, however, many different manufacturers of TPMS systems, including Continental, Schrader, and Pacific, just to name a few. Since there is no set standard for TPMS transmissions, each manufacturer has their own format. Some of them use different modulation schemes, center frequencies, baud rates, and place the serial number in different locations within the bitstream. Even for the same manufacturer, older vehicles may not have the same format as newer ones. Decoding and extracting the serial number from multiple different formats was the biggest technical challenge we faced this year. The applications of the system include targeted advertising and public safety. Targeted advertising is used in the form of electronic billboards that show specific ads to drivers on the road, and drive-thrus that can pull up the most recent orders or promotional items for customers. Law enforcement may also use this to track down lost and stolen vehicles if serial numbers are known to the police. Since it also allows for connected networks, Internet of Things is also viable. We identified different stakeholders and features for the design. The client, Nate Gergen, advertising companies, and law enforcement make up the stakeholders. They expected our system to be fast, affordable, and robust. Fast because it needed to extract serial numbers quickly enough so that multiple cars can be detected without a backlog. Affordable so that it has an advantage over typical vehicle identification systems. And robust to capture serial IDs from different formats. Now Chris will explain the high-level system overview.
The user starts the system through a GUI. The system's receiver will continuously record at center frequencies of 314 and 434 MHz, which are the transmission bands for TPMS signals. The recorded signal is then demodulated and Manchester decoded. The signal is characterized using specific metadata and cross-referenced with a lookup table to find what make, model, and year of the vehicle that the sensor came from. We were able to add 14 different formats to our lookup table, and we created the capability to add more formats in the future. If the make, model, and year of the vehicle is in our formats table, then the sensor's serial ID will be printed on the GUI for the user to see. The serial ID is also stored in a data log as well. We have 3 main branches in our code. To be able to record at 2 different center frequencies simultaneously, we had 2 RTL SDRs and antennas that record in parallel. This makes up the first 2 branches. Every 10 seconds, a recording for 315 MHz and 434 MHz is saved and sent to a queue for further processing. The last branch in the diagram is then used to demodulate the recording, extract metadata, extract a serial number, and log these results and print them all to the GUI for the user to see. Now here's a demo of our system. The system is continuously recording and processing data. The bottom right shows the GUI of our system. As you can see in the GUI, we were able to identify the TPMS serial ID. This is a screenshot of the GUI from the previous video with the decoded TPMS serial ID AA1817. Dutch will now explain the system functions in further detail.
The raw data that's read from the RTL SDRs are complex samples in rectangular coordinates as seen on the left. The first step in pre-processing is converting the samples to polar coordinates, but using the derivative of the angle instead of the pure angle. These 2 arrays are more convenient to work with because messages are embedded within the magnitude array for ASK and within the delta angle array for FSK. Both these arrays are anti-aliased and downsampled by a factor of 8 to reduce processing time. A final low-pass filter is applied to remove out-of-band noise while retaining resolution. Now that the signal has all out-of-band noise removed, we can identify where messages were transmitted by analyzing the magnitude array. The magnitude array is thresheld by a noise ceiling below which there shouldn't be any intended messages. The noise ceiling varies along with the current array being processed. We also disregard segments that are too short in length to possibly contain a signal. In this example, the big burst on the left is actually a sequence of many short bursts that did not pass the length check. After pre-processing, we are left with cleanly grouped messages that have minimal out-of-band noise. As a reminder, we're trying to extract the serial number from these messages. And in order to do that, we need to find 7 pieces of metadata that characterize the signal. The set of metadata is compared to entries in our lookup table, which tells us where to find the serial number. We could follow the magnitude and delta angle arrays as they pass through our system and metadata is found, but that would take too long. Instead, we're going to skip around to the functions whose mechanics are not obvious. As mentioned before, the message is embedded within the delta angle array for FSK and within the magnitude for ASK. We find a value we name the FSK threshold and is shown in the magnitude plots above as a red line. This value is meant to separate high values from low values. The magnitude of an FSK signal, as shown on the left, will remain a relatively constant high value. Ideally, 100% of FSK samples will fall above this threshold. The magnitude of an ASK signal, as shown on the right, will alternate between low and high values. And since all TPMS signals are Manchester encoded, 50% of ASK samples will fall above the threshold in ideal scenarios. Thus, halfway between 50% and 100% is the ideal cutoff for distinguishing an ASK from FSK signal. After experimental tweaking of both the threshold value and percentage cutoff, 60% produced most accurate results. After this step, you can imagine that the message component is threshold by its average to produce bits. Our system has to be able to find unknown bit rates. First, it counts consecutive values as shown in yellow and collectively names these values counts. Because we know that all TPMS signals are Manchester encoded and most of them have a primer that simply alternates ones and zeros, we can safely conclude that 1 bit is the most common consecutive value. The mode of counts is converted to bits per second based on sampling rate and downsampling factor. Finally, we use the bitrate to convert the array into individual bits. And now David will go over future improvements.
Our solution proves that the patent is possible, but is not in a marketable form. As Casper mentioned above, one of our system features is affordable. Even though we tried to achieve this goal, our current design did not meet this feature. The total cost of the system, an estimation of $7,548, far exceeds the $100 limit. This is largely due to MATLAB licensing. If the code can be portable to an open source platform, such as Python or C, the cost of the project would decrease substantially. On top of this, recording TPMS signals would also require an open source solution. Removing the need for a laptop would also decrease the cost. Going further, more research and experimentation is required to find out if the system can operate on a standalone platform, such as a Raspberry Pi. This will also help the system to be more deployable and potentially reduce the space needed. Since the TPMS sensor requires the vehicle to get up to speed about 25 miles per hour from testing to begin chirping, in situations where vehicle speed has never passed 25 miles per hour from the start, our system will be unable to detect a passing vehicle. The addition of a triggering device that forces the TPM sensor to chirp would guarantee that a passing vehicle chirps and transmits its TPMS signal in any given scenarios. As mentioned above, a lookup table is needed for our system to operate. So far, the data in the lookup table has been gathered through experimentation and reverse engineering. However, we could also purchase this information from the manufacturers to improve the accuracies and reduce time for our system. This would greatly expand our lookup table and increase the robustness of the system. This is our presentation. Thank you guys for watching.